So day 3 out of day 5, and representing functions numerically, graphically, algebraically, a lot of review in that. Determine the domain implied, and you were introduced to something new called relevant domain, which has to do with word problems and making sure that we tell people, you know, this is actually something we're supposed to be able to use. And then talking about range of a function, and that I think was more on Thursday and Fridays. So today, more talk about whether or not it's continuous or discontinuous, and then the type of discontinuity, removable, non-removable, jump, and infinite. And tomorrow, even more about that. Determine whether a function is increasing, decreasing, or constant. That's definitely in today's, not a hard concept, just something we have to get through. Then we've got determine if a function is bounded or unbounded. Again, not a hard concept, just something we have to understand and get through today. Identify local and absolute minimums and maximums. Well, we've already done that as we went through, so it'd be kind of a nice reminder of how we're going to find those. Determine a function's symmetry, even, odd, neither. Definitely today. We'll get to quite a few of those today. Determine if a function has any vertical or horizontal asymptotes. I was looking at the notes and thinking we're going to have to get to that tomorrow. You know, these last pieces down here. Analyze the end behavior of a function. That stuff we'll finish up tomorrow. So 1, 2, packed full of good stuff, and we are middle of the page where it says day 3. There's day 2. I gotta keep going. Yeah, Friday's notes had the piecewise functions in there that you guys didn't get to see last year because of our lovely spring. So hopefully when you watch that video, you're like, piece of cake. Piecewise is not so bad. You just break it up into the pieces. So day 3 is about increasing and decreasing functions. And what we have to do is realize that we read graphs just like we read words, and that would be from left to right. So as I look at this graph, the first thing that bugs me is, you know, the book never puts arrows on anything, but we have to understand that these are going to continue on forever. And then what you want to do is think, if I were drawing this graph from left to right, would I be going up? Then it's increasing. Would I be going down? Then it's decreasing. Does it stay flat? Is it horizontal? Then we've got constant. So this one, as we go from left to right, is increasing. And it is increasing all the time. It's ever so slightly in some spots, but it definitely is increasing as we go from left to right. This one, decreasing, going down. Again, ever so slight as I get to this bottom portion down here, but it definitely is continuing on to decrease. Whereas this one is just horizontal line. And that's our constant. So that's where our y values are not changing. So we have a big box down here that says definition of increasing, decreasing, and constant function. And I just explained it super easy, and you're going to look at this and go, oh my gosh, what is all of this saying? But in the language of math, it's trying to get across what's going on. So a function f is increasing on an interval. If for any 2 points on the interval, you go a little bit further in the x direction, and you're going a little bit further up. That's what it's saying. So a positive change in x results in a positive change in f of x. It has a positive slope. Then a function f is decreasing on an interval. If for any 2 points in the interval, a positive change in x results in a negative change in f of x. You go a little bit further to the right, and it goes down a little bit. The slope is negative. And a function f is constant on an interval. If for any 2 points on the interval, a positive change in x results in no change in f of x. So horizontal, the slope is 0. So what we want to do is explain to people when we have graphs that don't look normal, you know. We think of the normal ones as what we've studied in Algebra 2, and we get to this, and it's like, well, how does this show up? Because this is a piecewise function, is what's happening here. And again, even though they're not there, because the book uses those little snapshots, screenshots of what a graphing calculator or a grapher would do, we know that this is supposed to go on forever. And it says state the intervals on which the graph is increasing, decreasing, or constant. So if I'm supposed to read this from left to right, the first thing I do is see, well, this is going down. That's a decreasing interval. So for decreasing, my x values would be negative infinity up to negative 2. Now, intervals are written just like our interval notation, with some exceptions. First, you never have closed brackets on intervals of decreasing, increasing, or constant. And that's because a point cannot be increasing or decreasing. So we always just use the parentheses, our normal brackets that we use whenever we're talking about things that are not going to include our endpoints. So decreasing is from negative infinity to negative 2. Now I keep reading the graph and I see, oh, from here to here, that's a horizontal line. That's a constant. So constant would be from negative 2 to 2 in the x's. And then there's another change to the slope. And now from 2 to the right forever, that one's going to be increasing. And I know we've trained you pretty well not to use the book answers in the back of the book, but you need to know that there are a couple of spots in this book where things are just outright wrong. And one of them would be increasing, decreasing, and constant. When you look at that, do you see how they have square brackets? Yeah, and so when we first started teaching this, we're like, no, we don't use, nobody uses square brackets, so you can't have a point that's increasing or decreasing. We went to Mrs. LaRue and said, this is wrong, right? I mean, there's no increasing or decreasing here, and she said, yeah, that's wrong. They shouldn't be using square brackets on anything. So don't use the book as your guideline, you know. It was one of those things where we picked out every single book possible, and then people realized they forgot to pick out the pre-calc book, so they just stuck with Pearson because Pearson does all the other books. So there are some things that are not right in here, and this is one of them. Analyzing a function for increasing and decreasing behavior. That was a nice little picture they gave us back there. That was really helpful. So we realized it would be really helpful to have a graph so that we can look at what's going on with our functions. So for each function, tell the intervals on which it is increasing and the intervals on which it is decreasing. And you don't have to use a calculator if you know what it looks like. And this first one, I would hope we look at that and say, wait a second, I know that one. X squared, that's going to be a parabola. It has that a x minus h plus k thing going on. That means it's going to be shifted 2 to the left. So over here at negative 2 is where my vertex is going to be. And since it has a positive 1 in front of it, it's going to open up. Wouldn't hurt to pop it in the calculator as well, but I mean, that saves you some time on a test if you recognize one. So then I started thinking, this one's not going to have a constant. There is no stretch of this curve that comes out flat and horizontal. But as I read it from left to right, grab a different color here, that's decreasing from left to right. So my first interval is going to be a decreasing interval, and that's from negative infinity to negative 2. The rest of this increases. You know, it starts taking off over there. So increase from negative 2 to infinity. Now that's a pretty basic graph there. You know, it's a parabola, and we've studied that. We go over to B. We might not feel quite so certain about what that's going to look like, because this one has division then we should be thinking, ooh, this is going to be hyperbolic. And hyperbolas, I focused in college on hyperbolic functions. That tells you there's a lot of classes about hyperbolic functions. They do a lot of different things. So we could use tables, but really these kind of problems we intend for you guys to think a little bit about the zeros in the denominator, which is in tomorrow's lesson. Because those zeros that we see in the denominator cannot cancel out with anything in the numerator, they are going to be vertical asymptotes. So we're going to have a vertical asymptote at -1 and a vertical asymptote at +1. Which, you start thinking about what you know about hyperbolas, and you think, well, there's got to be branches out there to the left of -1 and out there, to the right of +1, and in the middle it's going to do something. Well, like I said, you could either make tables, or you could grab your calculator, just get a sketch of it, see what it looks like. So we need y equals, and we've got x squared divided by, and then you have to use parentheses, let the calculator know we're dividing by x squared minus 1. Graph. Oh boy, I had that one zoomed in for something. Last problem I was doing. Zoom 6. Okay, definitely hyperbolic. And so it looks like this. There's our two symmetric branches. And then in the middle, we have this kind of upside down parabola thing going on. And so what we would want to make sure of is, see how it's going up? Looks like it hits 0, and then it's coming back down. We'd want to go in the table real quick and make sure that 0, 0 is the top point there. And it is. There's our 0, 0. Now, since we're doing min and max anyway, we might as well give this one a try and say, second trace, number 4, I really want to know, is this 0, 0 right here as the top point? Now, you'll look down at the bottom, and your numbers might be a little different than mine, because it depends on where you hit your left arrow and where you hit your right arrow at. And you think, well, that's not 0, 0. It is. I love this. This is Blinky apologizing. Blinky said, I couldn't get you perfectly 0, 0, but here's what I got you. -0.00000129. Blinky, that's 0. And -1.61 e to the -12. I don't even want to say that one. -11 zeros, 161. Now your calculator may have said perfectly 0, 0, because it all depends on where you hit for the left and the right. So it's at 0, 0. Now that's important because I want to talk about those increasing and decreasing pieces. That's what we were supposed to do. So we read the graph from left to right, and I see, well, this one is increasing. So it's going to be increasing from -infinity to -1. Then, oh, look at this one. This one's also increasing, as I go from left to right. So that's going to be from, oh, goofy, -1 to 0, from here to here. Now, here's what I don't do. I don't put a union symbol there. These two are not together, as we would be talking about domain. They're separate pieces of the graph. We're just describing those separate pieces. Then it's going to go down, decreasing from 0 to 1, one of our vertical asymptotes. And then this other branch over here is also going down. That's decreasing from left to right. And that's from 1 to infinity. So, like I said, it's not hard. It's not difficult. It is one of those things that occasionally shows up on the ACTs because they want to know, hey, did anybody have a chance to get to talking about increasing, decreasing, or constant intervals? And sometimes it'll be in the form of a word problem, so they can ask you, usually it's about an airplane. A plane increases to a certain altitude, levels off for a while, then goes down or up depending on the air traffic controller telling them where they need to go. So as long as we can understand increasing, decreasing, and constant, we'll be fine. Feel okay with those? Looked like you were ahead of me when you were writing them down. Everything's good? Okay. So we need lots of arrows here. As we move to a topic called boundedness. So we're learning lots of different topics about graphical things in 1.2, and we're learning them in chunks of information. We just had a chunk on increasing, decreasing, and constant intervals. Now this one is about boundedness. If something is bounded, there's a cutoff, and it doesn't go above or below that cutoff. So as I look at this first graph, I realize, well, these arrows are going to go up forever, and these arrows are going to go down forever. There's no cutoff above it. There's no cutoff below it. So this one is not bounded above, and it's not bounded below. It's going to keep going forever. However, this one, the arrows are going up. But I could draw a helper line down here, a little horizontal line, that graph would never get to, and it would never go below. So that one is bounded below. There's a cutoff. Here's my lowest value for my y. This one over here, the third one, arrows show us going down forever, but we've reached the top, and that is bounded above. Now, you can only call a graph bounded if it is both bounded above and below. So these are kind of little descriptions, bounded above and bounded below, that will eventually lead us to a graph like this, which is bounded. So little descriptions of bounded above, bounded below, and then all together, if you have both of them, it's just called bounded. Ben. So just horizontal line would be bounded because it's not going to go up, it's not going to go down. It's just there, All right, so boundedness. Let's take a peek. Again, the math is going to sound much more complicated, A function f is bounded below if there's some number b that is less than or equal to every number in the range of f. Any such number b is called a lower bound of f. So that lowest y value, what's just below it? A little bit less than that. A function f is bounded above if there's some number b that is greater than or equal to every number in the range of f. Any such number b is called the upper bound of f. So what is that highest y value? And then a function is bounded if it has both, bounded above and bounded below. So now, like it says, we can extend the above definition to the idea of, what about just this portion of the graph? Not the whole thing, but let's just look at a piece of this graph. Is it bounded on a certain x interval? In the graph that we just had, this would be bounded above from the interval of -1 to 1. That little portion of the graph, not going to go above that, ever. So if we need boundedness, depending on the math that we have to do, can we make it happen? And the answer is yes, by restricting the domain, by saying from here to here only, just look at these x's. And as it says, we're going to restrict the domain of consideration in each part of the definition to the interval that we wish to consider. For example, the function f of x equals 1 over x. bounded above on the interval from negative infinity to 0, bounded below on an interval from 0 to infinity. This is our parent function for hyperbolas. That little baby right there. Because to be a hyperbola, you just have to have division. So it has division by the most basic thing we can divide it by, which is x. And if you remember, our vertical asymptote would be at the 0 of the denominator, which would be x equals 0. And then you just think, okay, so if I put 1 in there, I'm going to get 1 back, so it's going to be 1, 1. If I put 2 in there, it's going to be 1/2. So you're kind of making a table in your head. And then if you put some negatives in there, -1 would kick out -1. And -2 would kick out -1/2. Oh yeah, this is the hyperbola with the 2 symmetric branches. And I don't like that. In first and third quadrant. So there's our parent function right there. Now, what this says is it's bounded above on the interval from negative infinity to 0. Bounded above, negative infinity to 0. This chunk right here of the graph. Oh yeah, because it never quite makes it to the x-axis. Yeah, it's bounded above. And then the other branch of the graph, it's going to go up forever. I mean, we can see that. We've got the arrow here going up forever, but right here, never going to cross the x-axis. So that's from 0 to infinity. So with a really basic graph, our parent function for hyperbolas, we can see, yes, if you just look from here to here, it'll be bounded above. And from here to here, bounded below. So that's what our interval notation is telling us. What is that interval where this is happening? Now, checking boundedness. We want to identify each of these functions as bounded below, bounded above, or bounded. And for w of x, we see 3x squared minus 4. So hopefully you're thinking, okay, parabola, opening up. But this is weird because this is not in our, A, H, and K. Well, it kind of is. Kind of is. A is really 3, so that's a vertical stretch, factor of 3. H is 0. That's why we don't see any of that there. And then we see the minus 4. So if we were going to graph this by hand, which, by the way, you wouldn't have to because this, remember that the objective that we're trying to get to here is about boundedness. We would say, I'm going to graph 3x squared, and then I'm just going to move it down 4. But for this homework, for this on the test, we expect, in the end, you're going to plug her in and take a peek. So y equals 3x squared minus 4. There it is. Yeah, that's what you would have expected to see with a 3 in the front of it. It should be vertically stretched. And then you'd get a few numbers off of your graphing calculator, but like I said, for this, we really just want to know. That. Because we can see that our vertex is going to be down here at 0, -4, and we know the intervals are described by the x. We just really needed to know that x is 0 is where the change takes place. I mean, that's what's happening here. So with this one, going up forever, but we can find some pieces that would be bounded above, bounded below. So if, actually I'm thinking about increasing and decreasing. Right here we've got, this is going down, so we've got our decreasing, but they just want us to identify boundedness at this point. Know this is what I keep thinking. everything that we're doing in 1-2 is going to work together. By the time we're done with this section, we want to be able to graph these. We want to talk about increasing, decreasing, boundedness, asymptotes. All of those things are going to come together in one. So right now, we say, well, this is bounded below. But by the time we get to the test, it may just say, analyze the function, which means we have to go through all of it, all of the things that we can find. So this one is bounded below. It's not bounded above, so we can't say bounded. That's all we got. So we looked at the graph, and there it is. This one, getting a little more complicated. First off, that denominator, that's not factorable anymore. 1 plus x squared or x squared plus 1. So this one, yeah, we'd probably just put it in and take a peek. See, what does this thing look like? Remembering to use parentheses for our denominator. Wait a second. Must have punched something in wrong. That's supposed to be a hyperbola. It has division. It is a hyperbola. It's a weird one, but it's a hyperbola. So what I would want to do is get a little bit closer in to see. Looks kind of like it takes a little dip. Then it goes back up to 0, 0 and goes up a little ways and then comes back down. So I don't want all of those y's in there. Let's try -2 to 2. Well, isn't that interesting? It's still a hyperbola. It still has 2 branches that are symmetric to each other. It's just a strange little bugger is what it is. So we are below. Oh, better use a different color. Takes a little dip. Comes back up. Symmetric on the other side. Looks like so. And really, all we needed from this is bounded below, bounded above, or bounded. Is it bounded above? Is it bounded below? Then we just say bounded. And there it is. So, again, a big deal to be bounded. It's one of those things that we look at when you're talking about functions and whether or not you're going to be able to do things like differentiation and calculus. Boundedness is another thing where you spend a lot of time talking about it. And those points where it's turning up there, we used to call those turning points. You'll be calling those cusps. Just kind of strange little turns in a graph. Another concept. Check mark. Got that off the old objectives there. Boundedness. So on to something else that happens with graphs, something that we just took a look at a little bit ago, and that would be local and absolute extrema. Extrema are, where's the top of this graph? Where's the very tip top? Where's the very bottom point on it? Those would be absolute extrema, so for the graph overall. But we already know that you can have some local extrema, your local maxes and your local mins that happen. So these would be local maxima. They're turning points. And if you only look at a certain interval on the x's, those are your highest points. Oh, and yeah, it's missing its arrows again. Down here at Q, that would be a local minimum. It's not the absolute minimum because this arrow is showing this graph is going to go down forever. These two are not, well, this one would be considered the absolute maxima. So when you look at this, know that it can be a local maxima, and if it's overall for the whole graph the highest point, then it's also the absolute maxima. So we're going to write our answers in the following format. Our focus is on the y-coordinate. How high are we talking? How low are we going? That's why we're talking about them as maxima and minimum. So the max is whatever the y coordinate is at x equals, and then we give the x coordinate. So it feels a little backwards, but the focus for maximums and minimums is on the y, the highest and the lowest. So like I said, it can be local if you're just talking about on an interval. It also might be an absolute, depending on whether or not you're going to talk about the entire graph as you go through it. So that's what they're going to explain in the little math box here. Local and absolute extrema. A local maximum of a function f is a value f of c that is greater than or equal to all range values of f for some open interval containing c. So you define that. Do you want the whole graph? Do you want to talk about all x's? Or do you just want to talk about a portion of it so that you can find that local maximum? If f of c is greater than or equal to all range values of f, then f of c is the maximum or absolute maximum value of f. A lot of books just say maximum. They don't say absolute. So know that in the future, if somebody just says, what's the maximum of this graph, it's the same thing. Minimums, same concept. So you can have a local minimum of a function f is a value f of c that is less than or equal to all of those range values of f on some open interval containing c. It might be that it's a minimum or absolute minimum value of f if it's for the entire graph itself. So another thing to keep in mind, some books call local minimums, local maximums, relative maximums, relative minimas. So again, just a vocab choice, has to do with whatever book you're using at a given time. So now example 8 says, here's our job. Identifying the local extrema. Decide whether f of x equals x to the fourth minus 7x squared plus 6x has any local maxima or local minima. If so, find each local maximum value or minimum value and the value of x at which each one of those occurs. We have to use graphing calculators for this. I would love to tell you that by the end of the year, we will be able to do this by hand. You need calculus for it. So we definitely will be using our graphing calculators to take a peek at these. All right, away we go. Y equals x to the fourth minus 7x squared plus 6x. And I'm thinking as I'm graphing this is a quartic. The end behavior should be parabolic. It has a positive x to the fourth, so the end behavior should be looking up and up when I graph it. Zoom 6. Oh my, okay, so this has got a lot going on. I'll make a little sketch so that the people that are listening to the video here don't know what on earth it is we're doing. Oops, kind of like so. All right, so now, yeah, Ben. Oh, you got to fill out the thing in the Chromebook. All right, so I take a look at it and I realize this is going to be a local min. This is going to be a local min. And this, bless you, will be a local max. So we're going to say local min of blank at blank, and we're going to have to do that twice. And then local max of blank at blank. You might not be able to, Ben. I just remembered that rapid identity is down. Can you even get into your Chromebook? Oh, it's working. Cool. So let's see if mine is. There we go. So they got something working. All right, I'm sure you're already doing this. You know, we need to call on Blinky and let Blinky tell us what's going on. But first things first, if I can't see it, sometimes Blinky will find it for me anyway, but I want to know that we're doing the right thing. So I'm going to need lower y's. I'll try -20. See if that's enough. No! Still need more. So in my window, I'm going to try -30. Hey, there we go. So if I can see it, Blinky can find it for me. Second trace, and number 3. I always do these left to right. It's just a thing. You know, you wouldn't have to. You can find them in whatever order you want to, but be on the left side of the valley and hit enter, and then use your right arrow to move to the right side of the valley and hit enter. And we go 3 decimal places, so -2.057. Is my x value, and remember that's going to go at the end. My y is -24.057. Like so. Second trace, I think I'll do the maximum on my way over to the other minimum. Left side of the hill, enter. Right side of the hill, enter. Enter through guess. So our x value is 0.456. Oh, I put it in the wrong one. And our y, 1.324. And one more to go. Second trace, number 3. Left side of the valley, enter. Right side of the valley, enter. Enter through guess. 1.601 for the x value at the end, and -1.766 for that y value. So the y value comes first because that's what we're really caring about here. When we're saying max and min, we're trying to figure out what's the y value that we're interested in. So, like I said before, all of this is going to come together in a graph and just say, analyze, you know, find all of these things about this graph. Increasing, decreasing, constant, boundedness, local max, local min, all that good stuff, and more, because now we need to talk about symmetry, which was another objective. We're going to look at 2 types of symmetry in here. So we're not talking about all the symmetry that you studied back in geometry. We're going to talk about function symmetry, where either it's going to be an even function, an odd function, or neither. So how are we going to know? Well, if a function has symmetry with the y-axis, so if you could fold it over on the y-axis and get exactly the same thing on both sides, then it has even symmetry. But you have to show that algebraically. You know, we don't want to show that. I'm just thinking this is probably sucking up my battery power there while I'm yakking away and my calculator's running. We want to show this algebraically on a test. You know, we want to show that there's math that we can do for it. So what we do is we put a -x into the function. If, when we put a -x into the function, we get right back to the original, then it has even symmetry. Now, how does that work? Well, remember, f of x is y. And here's what we're saying. If you put in a negative x value, this will be the y value that you will get. If this is truly symmetric to the y-axis, it's not going to matter that you put a positive x in or a negative x in. You're going to get the exact same y value. So a negative or a positive kicks out the same y, and that makes it even. Over here, if you have an odd function, that's a function that has rotational symmetry of 180 degrees about the origin. So if we take this blue piece and kind of visually turn it, it'll match the green. Now what happens to the coordinates when you do that? Well, any xy becomes negative x, negative y. So what that's going to do for us is if we put a negative x into f, when we get done, it's going to be the opposite of everything that we saw. So our job is to put negative x in for everything in a function. And if we get exactly the same thing that we started with, we call it an even function. If we get the exact opposite of what we started with, we call it an odd function. Anything that's a mixture of the two, we just say neither. It's not even, it's not odd. Might be some other kind of symmetry, but we're not studying those. We're studying even and odd symmetry. So each of the things we're doing today has been a big chunk in knowing a lot of information about functions. Tell whether each of the following functions is odd, even, or neither. Well, x squared minus 3, without their graph, we would know, hey, that's a big parabola that's down there at 0, negative 3. That's going to be symmetric to the y-axis. That's even. But we don't want what the calculator tells you. We want what you can see algebraically. So what we do is put a negative x into the function wherever we see an x. So this will become negative x squared minus 3. And then we do whatever simplifying we can, which in this case is just, oh, well, negative x times negative x, that's going to be a positive x. And then we look at it, and we say, all right, I put a negative in there. Oh, look, I got the exact same thing I started with. So f of negative x equals f of x. That's what even is. So we've confirmed algebraically. Now most of the time this is backwards because on the test we're going to want to show this algebraically, and then maybe you'll plop it into your graphing calculator just to make sure that you got it. This one. Take a look at it, everybody. Does that look symmetric to the y-axis? No, ain't going to happen, is it? It's not perfect there. How about rotational symmetry, 180 degrees about the origin? If we take this piece and we rotate it 180 degrees, is it going to land right on top of the other part? So this one we would say, graphically, it appears to be neither. But again, it's the algebra that we want to see. What happens when you put a negative x into G? Well, let's see. There's two spots it's going to have to go. And then we have to simplify. Well, negative x times negative x will give us x squared. And then negative 2 times negative x will give us plus 2x. And then we have a minus 2. So here are the two things I'm looking for. Is that exactly what I started off with? No. Is it the exact opposite of what I started with, which would have been negative x squared plus 2x plus 2? No. So we were right. Yeah, neither's good. That's what it is. It's not working. So again, doesn't mean that it doesn't have some kind of symmetry. We can see that there is symmetry here. It's probably around the line x equals 1 or so, but that's not what we're talking about. It's either even, it's odd, or it's neither. That's it. So now, that monster. Take a peek at it. Does it look like it has some symmetry? Okay, over the y-axis? No? If I take this and go 180 degrees, hey, this might be odd. This 180 degrees, yeah, it's looking odd. So think about what that means. That means if I put my negative x in there, I should see the exact opposite of what I started with. So let's see if it works. H of negative x equals negative x cubed over 4 minus negative x squared. Okay? Negative x times negative x times negative x. Negative x squared, x cubed. Negative x squared, well, that's going to be a positive x squared. And then I compare it to what I started with. Oh yeah, it's got an extra negative on the top there. That means it was like it's multiplied by negative 1. So h of negative x equals negative h of x. We're right. It's odd. Now that last statement, this last piece, that's a big deal, you know, because that's how we're supposed to show that we understand when you put a negative in, if this happens, you have an odd function. So you pull it all together there at the end. So now, we have lots of extra examples here for even and odd. Let's see what we can get through. Extra example 9. Determine algebraically if the following functions are even, odd, or neither. We're not even going to bother verifying graphically. If you want to do that, feel free. But what I need to look at is what happens when I put a negative in there. What's going to happen? So this would be the negative of negative x squared plus 5. And hopefully it's starting to become intuitive to you. You're like, but if you raise it to an even power, it's just going to be positive anyway. So minus x squared plus 5. Oh, look what happened. It's exactly the same as what I started off with. So f of negative x equals f of x. That makes this one even. So even, odd, or neither. Go to B. Plug in a negative x. See what happens. Negative x squared minus 4 times negative x plus 3. All right, well, when you square it, it's just going to become x squared. But negative 4 times negative x is plus 4x plus 3. So now's the defining moment. Is it exactly what we started with? No. Is it the entire opposite of what we started with? No. So this one is neither. Remember, those are our only two choices. It's even, it's odd, neither. Try C. So what do you put down for an answer when that happens? I mean, it changed one of them. So what do we write? Yep, neither. Yeah, it has to either be exactly what we started with to be even, or everything has to be made negative to be odd. Oh, let's see, I don't think we need to do that one. Let's look at F. Let's look at F. Q of negative z. A lot of places for z to go. So 3 times negative z to the 5th minus 6 times negative z to the 3rd plus z divided by, whoops, I didn't put my negative z in there. 3 times negative z cubed plus 4 times negative z. Whew. I'll have to keep track of. All right, let's see. Well, if you raise it to an odd power, it's going to come back out negative. So negative 3 z to the 5th, but negative 6 times negative z to the 3rd will be plus 6z to the 3rd minus z, all over negative 3x to the 3rd minus 4z. Ugh, too many negatives. I'm going to pull a negative out of the top and the bottom and see what's left. So negative 1 factored out would be 3z to the 5th minus 6z cubed plus z over negative 1 times 3x to the, oh, and I made an x instead of a z on that one. Force of habit. Okay, well then the negative ones would cancel out. I'm going to come over here since I ran out of space, and it'll look like this. 3z to the 5th minus 6z cubed plus z over 3z cubed plus 4z. Wait a minute. Is this a deja vu moment, or is that what we started with? That's what we started with, isn't it? So what is this one? It's even. Q of negative z equals Q of z, so it's even. I'm going to stop there because I don't think I'll be able to do justice. The last one that is a little weird. I'll start tomorrow's video talking about H and I because those involve radicals. I want to make sure that we take a look at those. But boy, did we hit a lot of objectives today. Ooh, that was a lot of good stuff. So we are at day 3. And we took care of increasing, decreasing, or constant, bounded or unbounded, local and absolute min and maximum, and got a really good click on symmetry there with even, odd, and neither. So not a ton left. And we've got 2 more days to take care of it. And like it says, we've got some little extra worksheets there for day 4 and day 5. Because again, this section is incredibly important when we start talking about analyzing functions, which is in 1-3. So we definitely want to make sure we have a good handle on this.